From pi to infinity, the numbers that shouldn't make sense. Introduction. Mathematics may seem like a world of rules and order, but hidden within its elegant structures lie numbers that defy intuition, logic, and even the very nature of understanding. Some numbers hold secrets so deep they still baffle the brightest minds on Earth. These aren't just numbers for calculations, they're portals into mysteries of the universe, symbols of chaos, infinity, and hidden patterns. From constants that appear everywhere in nature to values that never end or repeat, each one tells a story stranger than fiction. In this video, we're diving into the most mysterious numbers in mathematics, numbers that show up in black holes, prime spirals, music, nature, and even your own DNA. Stick around till the end, because the final number on this list has implications that may reshape how we understand the very fabric of reality. 1. Pi. Pi, represented by the Greek letter pi, is probably the most famous rational number in history. It expresses the ratio of a circle's circumference to its diameter, a relationship that has fascinated humans for millennia. What makes pi mysterious is not just its use in geometry, but its endless, non-repeating decimal form, 3.14159265535, continuing infinitely without pattern. Mathematicians have calculated trillions of digits of pi, yet it still holds secrets, like the suspected, but unproven, appearance of every possible number combination within its sequence. Pi's bizarre nature extends beyond math textbooks. It appears in formulas across physics, engineering, and statistics, surfacing in calculations involving waves, the structure of atoms, and even probability theory. Its presence in these seemingly unrelated areas raises a compelling question: why does pi keep showing up everywhere? Some even believe pi holds keys to understanding the deeper structure of reality, as if it's embedded in the cosmic code of the universe. Yet, despite its fame, pi still resists full comprehension. No exact fraction can express it, and no pattern has been found in its digits, even after decades of digital computation. That level of randomness in something so fundamentally tied to order, the geometry of a perfect circle, is deeply paradoxical. How can such disorder arise from such pure symmetry? This contradiction has inspired countless mathematical investigations, artistic creations, and even spiritual speculation. Some see pi as the ultimate symbol of mystery in science, simple enough for schoolchildren to learn, but complex enough to stump the most advanced supercomputers. The more we understand about pi, the more questions arise. It's as if pi is not just a number, but a message, a reminder that even within logic and precision, there are realms that transcend human understanding. 2. Euler's number, denoted as E, is another mysterious constant that appears across the mathematical landscape. Like pi, it is irrational and transcendental, meaning it cannot be written as a fraction and is not the solution to any algebraic equation with rational coefficients. It begins as 2.718281828, but the digits never repeat or terminate, extending infinitely into numerical chaos. Yet, this chaos somehow governs the most ordered process in the universe: growth. In nature, E is the foundation of exponential growth. Whether it's population increase, radioactive decay, or the spread of a virus, E is always in the background. In finance, it appears in compound interest. In probability, it emerges in complex calculations involving randomness. The question is, how can one number govern such vastly different processes? Its power lies in its role as the base of natural logarithms, which helps solve equations involving rates of change. But beyond its utility, E possesses strange mathematical properties. For example, it's the unique number where the slope of the function y equals e to the power of x is always equal to the function itself. This self-replicating behavior almost gives E a lifelike quality, mirroring how things in nature grow or decay over time. Euler's number also plays a key role in calculus, especially when dealing with limits in series. Its relevance becomes even more profound when it appears alongside other constants in Euler's identity, e caret I pi, plus 1 equals 0, an equation often called the most beautiful in mathematics. This single equation links 5 of the most important numbers in math, including the enigmatic e. To some mathematicians, e feels less like a man-made invention and more like a discovery, an ever-present force in the universe that we merely stumbled upon. That it governs both order and randomness makes it one of the strangest constants we know. 3. The golden ratio, phi, known as phi or the golden ratio, approximately 1.6180339887. This number has been hailed as the key to aesthetic perfection. From ancient architecture and classical paintings to the spiral of galaxies and the proportions of the human body, the golden ratio seems to lie at the heart of beauty and balance. But why? What makes this number appear so naturally in the universe? Mathematically, phi is the positive solution to the equation x squared equals x plus 1. What's mysterious is its self-replicating nature. Divide a line so that the ratio of the whole to the larger part is the same as the larger part to the smaller, and you get phi. This recursive property makes it appear in the Fibonacci sequence and the arrangement of leaves, flower petals, and even DNA spirals. The golden ratio's presence in art and nature has led some to believe it holds mystical or divine significance. Renaissance artists like Leonardo da Vinci used it to craft what they believed were perfect compositions. Some scientists argue it's merely coincidence, while others suggest it's a fundamental pattern embedded in biological and physical processes. What's even more curious is that phi often arises unexpectedly in math problems that have no clear connection to geometry or nature. It shows up in continued fractions, algebraic equations, and even chaotic systems, suggesting its influence stretches far beyond human-made aesthetics. Despite its beauty, the golden ratio refuses to be pinned down. Its irrational nature makes it impossible to write exactly, and though we see its pattern everywhere, its origin remains an enigma. Is it nature's signature? Or just another coincidence in a world full of patterns? 4. I. The imaginary unit I, defined as the square root of -1, may sound like a contradiction. After all, how can you take the square root of a negative number? For centuries, this was considered impossible. But in the 16th century, mathematicians embraced this impossible idea, and in doing so, unlocked a whole new dimension of mathematics. While I doesn't exist on the number line, it's the cornerstone of complex numbers, numbers in the form a plus b, where a and b are real numbers. At first, complex numbers were mathematical curiosities. But soon, they revealed the new truths in physics, engineering, and quantum mechanics. From electric circuits to wave functions, I became indispensable in describing the real world. What's particularly strange about I is how it behaves. Raising I to increasing powers produces a repeating cycle, I, -1, I, 1, and back to I. This cyclic nature suggests a hidden symmetry and has made it crucial in trigonometry and signal analysis. It's as if I operates in a shadow realm, governing patterns that real numbers alone can't explain. Perhaps the most famous appearance of I is in Euler's identity, e caret I pi, plus 1 equals 0. This equation ties together 5 of the most fundamental constants in mathematics, 0, 1, e, I, and pi, into one elegant relationship. Why these constants should be connected this way remains a profound mystery. I challenges our understanding of what numbers even are. It reminds us that math isn't just about counting or measuring, it's a language with symbols that can describe invisible realities. And sometimes, embracing the impossible reveals the most powerful truths. 5. 0, 0 at first glance, 0 may seem like nothing, literally. But this symbol for nothingness is one of the most powerful and controversial ideas in the history of mathematics. Ancient civilizations like the Babylonians and Romans had no concept of 0. It wasn't until Indian mathematicians introduced it as both a placeholder and a number with its own value that zero began to revolutionize how we understand math and reality. What makes zero mysterious is how it represents both absence and balance. It marks the boundary between positive and negative, but it's also the additive identity, a number that changes nothing when added, yet transforms equations when used in division or multiplication. Divide by zero, and you get an undefined or infinite result, sending systems into chaos. It's as if zero hides a singularity, an idea so potent that it breaks the rules. Zero is essential in modern mathematics. It underpins calculus, algebra, and binary code, the very foundation of computers and digital life. Yet, philosophically, it has puzzled thinkers for centuries. How can nothing be something? How can a void have a symbol and a function? This paradox has led to debates that cross into metaphysics and theology. Moreover, zero plays a central role in the equations that describe the universe. In black hole physics, zero volume meets infinite density. In thermodynamics, zero entropy is a state of perfect order. These aren't just abstract ideas, they describe real phenomena in the cosmos. Zero, in many ways, is where math meets the edge of existence. Far from being just a placeholder, zero is a portal to the unknown. It marks the boundary between the tangible and the abstract, the physical and the theoretical. Understanding zero might be the key to understanding everything. 6. Infinity. Infinity is not a number, it's a concept. But in mathematics, it behaves like a number in ways that are both fascinating and terrifying. Infinity represents something without bound, something that goes on forever. It shows up in calculus, set theory, and cosmology, where it helps us understand limits, sizes of sets, and the shape of the universe. But can you truly grasp the idea of something that never ends? One of the greatest mysteries of infinity lies in its paradoxes. For example, Hilbert's hotel is a thought experiment involving a hotel with an infinite number of rooms. Even if it's fully occupied, it can still accommodate more guests. This isn't just a brain teaser, it reveals how counterintuitive and strange infinity really is. Our finite brains struggle to wrap around something that defies all physical limits. Mathematician Georg Cantor revolutionized how we understand infinity by showing that there are actually different sizes of infinity. Some infinities are bigger than others, like the difference between the set of all whole numbers and the set of all real numbers. These ideas shattered old mathematical assumptions and opened up entirely new fields of logic and set theory. Infinity also appears in the calculus of limits, where a value can grow closer and closer to a certain point without ever reaching it. It's used to define areas under curves, the behavior of functions, and the summation of infinite series. In physics, it even crops up in the form of singularities, where space and time themselves collapse into a point of infinite density. Yet, despite all its uses, infinity remains elusive. It's an idea, not a number. A destination you can approach, but never reach. To work with infinity is to engage with the unknown, a concept that stretches the boundaries of logic and challenges the limits of imagination. 7. Prime numbers. Prime numbers are the building blocks of mathematics, yet they are among the most mysterious elements in all of number theory. A prime number is only divisible by 1 in itself, and at first, they seem easy to understand. But as you explore further, primes start behaving in strange, unpredictable ways. Their distribution is irregular, and no formula can perfectly predict where the next one will appear. What makes primes so fascinating is how essential they are, and how elusive. Every whole number can be built from primes, like how molecules are built from atoms. Yet, despite being fundamental, we still don't fully understand their pattern. The prime number theorem gives an approximation, but the gaps between primes fluctuate in ways that still stump mathematicians. One of the most famous unsolved problems in mathematics, the Riemann hypothesis, deals with prime numbers. It's believed that solving it would unlock a deeper understanding of the prime's distribution, but no one has been able to prove it since it was proposed in 1859. The mystery is so profound that there's a $1 million prize for its solution. In practical terms, primes power modern cryptography. Encryption systems that secure your internet data rely on the difficulty of factoring large prime numbers. The very randomness that makes primes hard to predict also makes them perfect for security. They are hidden keys that protect your digital life. Prime numbers sit at the intersection of simplicity and chaos. They're basic yet baffling, finite yet infinite in supply. Each new discovery about primes doesn't close the book, it opens a new chapter in one of math's deepest mysteries. 8. Graham's number is so large, it defies not just understanding, but imagination. It's not just big, it's beyond astronomical. This number arose from a problem in a branch of math called Ramsey theory, which deals with finding order in chaos. Mathematician Ronald Graham discovered it while studying how connections between points could be arranged in a way that avoids certain configurations. What's baffling is that Graham's number is so huge, you can't write it out in ordinary notation, not even in scientific notation. It's described using a system of up-arrow notation invented by Donald Knuth, just to express numbers of this magnitude. To put it in perspective, even if every particle in the universe were used to store digits, we still couldn't write Graham's number in full. Despite its unimaginable size, Graham's number is finite. That alone is mind-bending. You can perform calculations with it, reason about its properties, and use it to answer specific questions in combinatorics. Yet, the final digits of Graham's number, some of which are actually known, can be calculated. It's a paradox of scale, a number too big to fully grasp, yet precise in its tale. Graham's number forces us to think differently about scale. It challenges our assumptions about what large means and shows that mathematics can reach far beyond the physical world. In many ways, it's a concept designed not for calculation, but contemplation, a monument to mathematical creativity. This number's very existence pushes the boundaries of what our minds can comprehend. It stands as a reminder that the universe of numbers is not just vast, it's infinite in possibility. 9. Chaitin's constant, Chaitin's constant, known as Ohm, is perhaps the most mind-bending number in all of theoretical computer science. It represents the probability that a randomly generated program will halt, a concept that comes from the infamous halting problem posed by Alan Turing. What makes Ohm unique is that it's both real and unknowable. Its digits encode the answers to an infinite number of yes or no questions, but paradoxically, we can never compute all of them. Ohm is not just irrational, it's algorithmically random. That means there is no pattern, no compression, and no formula that can reproduce its digits. Every new digit of Ohm carries genuine new information, unlike most numbers in mathematics which follow some structure or rule. It's the purest form of randomness known to math, yet it's grounded in logic and computation. This number reveals the limits of formal systems and the boundaries of knowledge itself. Gregory Chaitin, the mathematician behind it, showed that within any mathematical system, there are truths about Ohm that cannot be proven within that system. In essence, Ohm formalizes the idea that there will always be things we cannot know, no matter how intelligent we become or how powerful our computers are. Its existence is a mathematical form of Gödel's incompleteness theorems, an embodiment of the idea that some things are true but unprovable. Unlike pi or e, we don't just lack the tools to find more digits of Ohm, we are fundamentally barred from doing so. No amount of progress will ever give us full access to its sequence. Chaitin's constant is not a number for calculation, it's a philosophical monument to the limits of knowledge. It shows that even in the realm of pure logic, mystery remains. Some numbers aren't just hard to understand, they're impossible to know in full. 10. The Feigenbaum constants, approximately 4.6692 and 2.5029, are lesser known but deeply mysterious numbers that emerge from chaos theory. They describe how complex systems shift from order to chaos through a process known as period doubling bifurcation. This might sound technical, but what it means is astonishing. Systems as different as dripping faucets, population dynamics, and electrical currents follow the same path into chaos, governed by the same universal numbers. The first constant, delta, approximately 4.6692, determines how quickly these bifurcations happen as a system becomes more chaotic. No matter the system or its scale, if it follows the same basic nonlinear rules, the transition into chaos will follow this constant. It's a numerical fingerprint of chaos across reality. What makes this so mysterious is the universality. Why should a number describing the transition to chaos in a chemical reaction also apply to a galaxy's spiral formation or economic cycles? The Feigenbaum constant suggests that chaos isn't random at all, it's structured, predictable, and beautifully mathematical beneath the surface. These constants were discovered not through experimentation, but through observation and computation. They weren't theorized first and then confirmed. They emerged from patterns found in real data. This flipped the usual scientific method on its head and revealed something truly profound. Math doesn't just describe the world, it can predict its descent into disorder. The Feigenbaum constants whisper a strange truth, that even chaos has rules. That beneath the turbulence of storms, stock markets, or neural networks lies an elegant framework, a quiet rhythm guiding everything toward unpredictability. From the circular perfection of pi to the unreachable depths of Chaitin's constant, the most mysterious numbers in mathematics remind us of a profound truth: the world we live in is not only governed by numbers, it is made of them. These aren't just tools of calculation, they're bridges to understanding reality itself. Some numbers, like E and phi, reveal hidden patterns in growth and beauty. Others, like I and infinity, stretch our definitions of logic and existence. And then there are those that question the very possibility of knowledge, symbols of what we cannot know, no matter how far we push the boundaries of thought. Each of these numbers exists independently of human invention. We didn't create them, we discovered them, like explorers finding ancient ruins etched into the fabric of the cosmos. They remind us that the universe is not just a chaotic collection of matter, but a structure with deep, mathematical roots. Numbers guide everything from the spin of electrons to the structure of galaxies, from the code in your computer to the DNA in your cells. So the next time you think of math as something dry or lifeless, remember this: embedded in its symbols are mysteries older than humanity and possibly deeper than the universe itself. The most mysterious numbers are more than digits, they are clues to a reality far stranger than we ever imagined. Stick with us for more journeys into the unknown. And remember, in math, as in life, what you can't see might just be the most powerful of all.